Alright, as it turns out, I forgot to press the record button when I was doing this in the lab. So here I am doing this all over again. So let's kind of check this out. Alright. So we'll go ahead and start with question number 1 again. And this time I'm not going to go for like the full explanation because we kind of explained that in the lab already yesterday. This is just really for the record. So we'll just do a translation, 1-to-1. We have a LDI. Okay, let me use a smaller one. LDI B0 before the loop, and then for the loop we have while begin. And inside the loop we have a condition. If a is greater than 0, we stay in the loop. So one quick way to do it is to do an AND AA, because if a is non-zero, then it has to be greater than 0. If a is non-zero, it has to be greater than 0 because a is unsigned. So this will check whether a is non-zero or non-zero. If it is 0, we get to the end. We get out of the loop. So we go to while end or while exit. And then in between we got the actual code for the loop. And then we have an unconditional branch JMPI back to while begin. And then after that unconditional branch, we have our while end as a label definition. So that makes the loop. So what is inside the loop is the rest of this program. Okay, so now we have to write the conditional statement. We have to use a register that is not used elsewhere in this code. So there will be LDI, I think register D is free. And then we do an AND operation. Now in this one, it has to be DA because we don't want to modify register A, but register D we can modify it. And once again, we have a JZI. If the result of the bitwise AND is 0, we go to AND if. Otherwise, we got some stuff to do here. And here's the AND if label. And then after the AND if, we have a right shift by 1. So once again we do LDI D1, and then we do a right shift register A by D amount, and then we have C being left shifting. So left shifting is the same thing as adding the register to itself, because it's the same thing as multiplication by 2, which is the same thing as that thing added to itself. Alright, so in here we have B plus equal to C, which is a pretty simple thing to do. It really is just add BC. So that's for question number 1. For question number 2, we have to first perform the bitwise AND. So we have to identify things. The first thing we have to do is to get this part done, and then the second part is the conditional branch of if the result is a 0 or non-zero, then we want to branch. Okay, so we want to say z equals 1, then we want to branch. Alright, so the first operation is to perform the bitwise AND. So we know the ALU has to be enabled, and based on what we know, let me see if I can get to the okay, we can, that's good. So we want to get to LogicSim. So in LogicSim we can see that inside okay, so let me see if I can do this. I don't have a way to right click with just the stylus. There we go. There we go. Alright, so we want to perform a bitwise AND. So we can see that this is the AND gate here, and the AND gate tracks back to operation 4 because this is output 4 of this particular demultiplexer. Alright, so knowing that, okay, now we want to switch back to Zerno. There we go. So we need the operation to be number 4. We also know that we want to have a constant one going into the ALU. So let's check back to the ALU, to Logisim. Where is it? Okay, maybe I'll do it in a slightly different way. I'm folding up the keyboard so I have access to the keyboard to do certain things that the keyboard is better at. I could probably use an external keyboard on the side. Okay, let me do that instead. Okay, so I'm going through a lot of background stuff here to kind of attach an external keyboard to the computer. So this way, for stuff that is best done on the keyboard, I can do it on the keyboard. Yeah, just takes a little bit plugging in. Let's see. Yep, I think we do have a USB port. There we go. Okay, so I have a keyboard on the side now. That makes it kind of easy to switch around things a little bit. So we want to switch back into Logisim, and this time we want to go back to main. Okay. And I think I just lost my stylus in all that operation. Okay. Okay, stylus is right here. Okay, got it. So we want to go back to main, and let's see if I can double click with a stylus. I don't think it's going to be easy here. Nope. Okay, let me see. Double tap, that works. Okay. So on this, in this diagram, we want this constant of 1 to go through this multiplexer into. So that means FC has to be a 1. And if FC has to be a 1, then RO1 demux and ALUEN both need to be 1. Okay. So switching back to Zernal. So RO1 demux has to be a 1, like that. And the select doesn't really matter because none of the register is going to connect to into once we have a constant connected to into. So this is going to be a cross. Okay. Register 0 is important because we need to route register 0 to input 1 of the ALU. So now we track input 1 to this demultiplexer. So we need register output 0 to be enabled, and we also want register output select to be a 1 in order to connect out 0 to the ALU in 1. Okay, so register output 0 enable should be a 1, and then the demultiplexer also needs to be 1. And then the register, in this case, is register 0 because it's register A. This operation does not update register A. So register input enable should be a 0. Then the select doesn't really matter because nothing is getting updated. The multiplexer does not matter because we are not updating anything. So it can come from anywhere. RAM select is a 0 because we are not using it. So RAM load can be a question mark because it doesn't really matter when RAM is not paying attention. Address mux is the same way because RAM is not being used. The program counter is not being used. Oops, okay, I take it back. So that needs to be a 0 to indicate that we are not updating it. But PC mux is now a question mark. IREN should be a 0 because otherwise we'll be updating the instruction register. That's only done when we are doing a fetch operation. The most significant bit of the ROM should be a 0 because otherwise it will reset the microcode pointer. And then the second last bit should be a 1 so that we can increment to the next location. So that now that we have the AND operation performed, the next one is to do a conditional branch, which is basically just JZI. If you know the configuration of JZI, you can just kind of copy it here, with the exception that you also need to know which bits are not chars. And I just lied because if it's not char, it has to be a cross, not question marks. So all of these question marks should be crosses for this particular version of the test. Okay. So we put our crosses here. Okay. All right, so let's go for the conditional branch. So the conditional branch is updating the program counter. That's the whole idea of branching, is we're updating the program counter. So PCEN has to be a 1. Then, okay, let's go back to the diagram here. And then this time we want to look at how the program counter is updated. EN is on already, but we know that we don't want to do the increment, which means PC mux. Well, sometimes actually we do want to increment, but whether we're incrementing or not depends on the Z flag. And the Z flag, if you look into the ALU, the Z flag is bit 1, and you can tell that it's bit 1 because when you track down Z out, it goes through bit 1 of the splitter into the output pin. So now that we know that it's pin 1 that we need to look at out of the flags register, so we need this multiplexer to select input 1 to become the output, which is PC mux here. That means PC mux needs to be 1. Okay, so PC mux needs to be a 1. Where we are going to ram to grab that next location is determined by the program counter itself. But we need to look at this multiplexer to see how we can connect the program counter to the address port. And we can see that ADDR mux needs to be a 1 to do that. So we know that this needs to be a 1. ALU operation can be unknown because we are not doing anything. So ALU EN is a 0. We are not using any registers. So this multiplexer can be a cross because we're not using it. This we are not using it either. And then register 0 also it's not being used. So this has to be a 0 so that we are not driving the demultiplexer. And if we are not driving the demultiplexer, then demux can be a cross, and then what register we are selecting inside the register bank can also be an X here. We are not updating any registers, so this has to be a 0, and this is going to be a cross, and this is going to be a cross because we are not updating any registers. We are accessing RAM in this case, so RAM select has to be a 1, and then RAM load also has to be a 1 because it's a read operation. IREN should be a 0 because we are not updating the instruction register, and just like with the previous instruction, we are not ready to reset the microcode pointer back to 0, so the most significant bit of the ROM slice has to be a 0. And then the most significant slice, second most significant slice, also needs to be a 1 so that we move on to the third slice. And that answers this question. Now, I did acknowledge that using this configuration, the register, the flag register is actually not going to be updated because the enable is a negated version of FC. So when FC is a 1, the flags register is not going to be updated. So I'm going to grade it accordingly. Basically, So I'll grade it accordingly because I made a mistake there. Question number 3. So with question number 3, the main concern here is that we have to find out what this bit pattern is representing. So I'll just go ahead and rewrite it here. 47A 0 0 2 0 1 0, and then the rest are all zeros. So we have a 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, and then 0, 0, 0, 0. And then the rest are all zeros. So now we need to figure out what bits is which bit. This is the sign bit, and the multiplier in this case is 9, which is positive. We're not changing the sign. The next 11 bits, this portion here, that's my exponent, which is biased. But I'm just going to keep it the way it is at this point, which is just 4, 7a. And then this part here is actually the fractional mantissa. So that means my actual mantissa is 1.0000, 0000, 0000, 0010, 0000, 0001, 0000. Okay, so that's my actual mantissa. And then you have to make use of the clue, which is basically saying if you get a multiplier, you can always express it as a sum of powers of 2 for the multiplier itself. And by the way, there's an x here for x plus 1x. So in this case, 9 is 8 plus 1. So it is the same thing as 2 to the power of 3 plus 2 to the power of 0. So as a result, we need one of these, but we also need to have one version of the mantissa that is multiplied by 2 to the power of 3. But when you multiply a binary number by a power of 2, you're really just shifting the point around. So that's why in this case, we have 1, 0, 0, 0 point, okay, because we're shifting the bits around by 3. So this 0 becomes this 0 here. And then the way I'm going to write this is, okay, maybe, okay. So everything is shifted by 3. So what is going into this position is this 0 here. So we have 0, 0, 1, 0. And then this 0 goes here. 0, 0, 0, 0. And then 0. And then this 0 goes here. So we got 0, 0, 0, 1. And then we got 0, 0, 0, 0. And then the rest are all zeros. Okay, so now we add these two, and I made sure that we don't need to actually do carry, so it's easy to kind of add these numbers. So we basically end up with 1, 0, 0, 1 point, and then 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, and then the rest are all just zeros. Okay, so now that we have this mantissa, we can see that this mantissa is not normalized. So we need to move this binary point 3 places to the left. But by doing this, we are dividing the mantissa by 8, which means we have to compensate for that using our exponent. So we have to add 3 to the exponent. So that's why the exponent needs to go to 4, 7. So B, C, and D, right? So 4, 7, D is the new exponent. And then the new mantissa is going to be, okay, so I'm just drawing, the boundary for each block of 4 bits. So we have 0, 0, 1, 0. We have 0, 0, 0, 0. And we have 0, 0, 1, 0. And then we have 0, 1, 0, 0. Then we have 0, 0, 0, 1. And then we have 0, 0, 1, 0. And then the rest are all zeros. So now when we combine all of this, the new number is going to have a underlying bit representation of 47D, which is really just copying this part. And then we have a 2, 0, 2, 4, 1, 2, and then a bunch of zeros. So this is accounting for 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. So we have 7 more digits because we need to have 16 digits to make up 64 bits. So we have 1, 2, 3, 4, 5, 6, 7. So that would be the answer for this particular question. Alright, moving on. This is for decompiling the code. So for decompiling this code, we're gonna start with the simple stuff. So that's C equals to 8, B equals to 0, A equals to K1, and then we have D equals to K2. And then we have a while loop. The reason why I know it's a while loop is because we have a branch from here all the way back to the beginning. So a backward branch always indicates that we have some kind of a loop. And we know this is a while loop because we check a condition here so that we can conditionally go out of the loop. So that's why we know it's a while loop. So we say while. The condition to stay in the loop is simply that C is non-zero. So we just say while C. And then we have some kind of code in the loop. And then after the loop, there's just the halt instruction, so there's no need to document it. So now we have to find out, okay, what goes into the loop. So what goes into the loop would be this portion of the code here. So that starts with add BB, okay? And add BB can be done by B gets B plus B, okay? We're literally translating it, okay? And then we have conditional branches again. This is a conditional statement because the conditional branch is forward, not backward. There's no unconditional branch going backwards. All the branches are going forward. So we have a conditional statement. And then we are looking for the reason or how we can get to the add BD instruction. So we get to label L2 if A has the sign bit set. So we can say, A is less than 0. But if you choose to do it this way, you have to indicate that A is signed. Okay, so that's important. So now that we know that, let's check out what is in the loop. In the conditional statement. In the conditional statement, we only have add BD. So that translates easily to add B plus equal to D, which is a compound assignment statement. And then after that, we have add AA, which is doubling the value of A. So A gets A plus A. And then we decrement C, so we can just do a decrement C like that here. So this is the code that is inside the loop. And that's the conclusion for this particular question, which is question number 4. So now we're moving on to question number 5, which is kind of tedious, okay? But just because it's tedious doesn't mean that we cannot do it. So what we'll do is we'll just go ahead and expand it. Okay. The mouse feature of my keyboard, external keyboard, is not working. But the keyboard itself is working because I can do this. So that is kind of strange that it's not letting me use the mouse feature. So let me see how I can open up a new journal. There we go. Okay, I can still do it, it's just a little bit harder now. Okay. So we now need to track down the operation of the code, and for each line, we need to indicate what it's doing. So line 1, it's just, C gets a value of 8. Line 2, B gets a value of 0. Line 3, A gets a value of K1. And then we have to find out exactly what K1 is. So K1 is 9, and then K2 is 8. So we got 9 and 8 here. Okay. So we got 9, and then D is 8. Okay. And then line 5 doesn't really do anything, so we skip to line 6. And CC, so C does not really get changed. But then we also have to say the Z flag is going to be cleared. The sign flag is going to be cleared in this case. All the other flags are preserved, so we don't say anything else. Line 7 doesn't really do anything. If you want to do something, you just say PC equals to L1. So now we continue execution at L1. Nope, I take it back. We are not branching because the Z flag is a 0, so no branching. And then we get to line 8. Line 8 is doubling the value of B. So B is getting double, but since it was 0, twice of 0 is still 0. Line 9 is AND AA. So A is 9, so A is still 9. Z is 0, sign is 0. Then we got line 10. JSI, the sign bit is a 0. We are not branching to L2, so instead we'll be branching to L3, which is on line 14. Line 14 itself doesn't do. Okay, so we go to line 11. Line 11 doesn't do a single thing. We get to line 15, which adds A to A. Register A has 9, so now it has 18. So A is now 18. And then line 16 is decrementing C. C becomes 7. And then we go back to line, we go back to label L0, which in execution is line 6. So if this is one iteration, but if you look at the previous line 6, this is pretty close. Okay, so we're really just looking at register C again. Register C has not changed. It is still okay, it has changed. I just forgot to update who is now 7. C is now 7. There we go. So when we go back to line 6, C is 7. This register C. Z is going to be a 0. And the sign is still going to be a 0. And then line 7 doesn't do anything. Line 8, B is still a 0 because no one has changed it. So B is still 0. On line 9, we also have to say what happens to all the other flags. There's no carry to this addition. The result is in fact 0. The sign flag is a 0. The overflow flag is a 0. And then the L flag as a result is also a 0. Okay, so this is going to be the same. So there's just a whole lot of copying. There we go. And then when we get to line 8, we are adding A to A. Okay, did I skip something? Nope, I'm good. Okay, so we get to line 8, line 9. A is ANDed with itself. So A is still 18. As a result, the 0 flag is cleared. The sign flag is also cleared. And then after that, we get to line 10. The sign flag is cleared, so we are not doing a conditional branch to L2. We get to line 11, which would do a unconditional branch to L3, which is on line 15. So on line 15, we continue execution. We are adding A to A, so A is now 36. And then followed by the rest. So so after this addition, C is there's no carry. Z is cleared. Sign is cleared. Overflow is cleared, and then L is also cleared. So 36 is really in the same boat. So we're just kind of copying all of that stuff here. All right. So moving on. So we get to line 16. It decrements C. C is now 6. We go back to line 6 now. After line 17. So there's a line 17 between line 16 and line 6. So when we get back to line 6, it's kind of doing the same thing. C has not, C is now 6, so C is still 6, but when we end it with itself, we have to clear the 0 flag and also clear the sign flag in this case. And then we get to line 7. Because the 0 flag is cleared, we are not taking that branch. We get to line 8. B is added to itself, so we look up B is still 0. Okay, so B is still 0, which means we just copy this entire row back here. C is 0, Z is 1, sign is 0, overflow is 0, the L flag is also 0. After line 8, we get to line 9 and AA. Okay, so where's A? A is 36, so A is 36, so there's no carry, whoops, because we're ending, so that means we only need to update the Z flag, which is cleared, and also the sign flag, which is also cleared. Then we get to line 10. Line 10 is a JSI. Because the sign flag is a 0, we are not branching. Then that means we go to line 11, which branches to label L3. So we skip to line 15. Add AA. AA is, so register A is now 72. There's no carry. The 0 flag is cleared because it is non-zero. The sign flag is cleared. The overflow flag is cleared. And then the L flag is also cleared. And we get to line 16, decrement C, so C is now 5. And we get to lines 17, which goes back to line 6. Okay, so line 6 is going to end C again, so C is, register C has a value of, oh, this is C, not B. Okay, so it's 5, so C is still 5. Which means the 0 flag is cleared, the sign flag is cleared, and we get to line 7. We are not going to perform the branch, which means we get to line 8. We double the value of register B. Register B is still 0, which means after this, the C flag is cleared, the Z flag is 1, the sign flag is cleared, the overflow flag is cleared, the L flag is also cleared. Then we get to line 9 and AA. So register A is 72. It is still 72. So we set the carry flag is, oh, this is an AND operation. So it only affects the Z flag, which is cleared, and also the sign flag, which is also cleared. We get to line 10. The JSI is not going to branch because the sign flag is a 0. So we get to line 11, which is an unconditional branch to L3, and L3 is leading us to line 15. We add AA. So register A has a value of 72. So now A has a value of 144. So then what we do is we set the flags. So the carry flag is still cleared, the Z flag is cleared, the sign flag is set because 144 is greater than or equal to 128. So the sign flag is cleared, the overflow flag is cleared. Wait, the overflow flag is actually set in this case, and then the L flag as a result is also a 0. So this is based on the overflow flag is a 1 because 144, the binary representation of 144 actually has the sign bit turned on, which basically means that what am I saying here? Which means we're adding a positive value, which is 72, to a positive value of 72, but we end up with a value that is negative if we choose to look at A as signed. Okay, and then after that we go to line 16, decrement C, so C becomes 5, becomes 4. Okay, and oh, by the way, the decrement instruction actually does not change the flags at all. So everywhere we have line 6, the flags are not modified. Okay, so we cross this out. Okay. Alright. So, and then we get to line 17. Line 17 is a JMPI to L0, so we get back to line 6 again. And let's see, we'll make a new page. There we go. Alright, so when we get to line 6, we are going to end CC. So C is now 0. So we say the register C is 0. Nope, take it back. C is 4. Okay. The Z flag is cleared. The sign flag is also cleared. And then we get to line 7, JZI. We are not taking that branch. Then we go to line 8. Add BB. So B is 0. And as a result, there's no carry. Z flag is 1. Sign flag is cleared. Overflow flag is cleared. The L flag is cleared. Line 9. Now we got something interesting. Because A is 144. The Z flag is still cleared, but the sign flag is set. So finally we got something to do. So finally we go to line 10, and line 10 is actually going to branch to label L2, so we now continue on line 12. So on line 12 we're adding B to D, so B is updated to the same value as D. And where's D? Register D has not changed all this time, so it still has the original value of 8. Okay, so put 8 here. But because this is an addition, it also changes all the flags, or it updates all the flags. There's no carry. Z is cleared, sign is cleared, overflow is cleared, and then L is also cleared. And then after that, we get to line 15, which add AA again. So 144 plus 144 is 288. But 288 cannot be represented in A bits. So you have to basically store 288 minus 255 to minus 256. So the actual value being represented is 32. Okay, that looks right. But that means, but this time carry is going to be a 1, because we are adding 144 to 144, and the result cannot be represented using A bits, unsigned. So carry is going to be a 1. Z is going to be cleared. The sign flag is also going to be cleared. The overflow flag is going to be cleared. And then, let me see. The overflow flag is, let's see, we're adding 144 to 144. Nope, the overflow flag has to be a 1, because the sign doesn't make sense anymore. So the L flag is actually going to be a 1 in this case. And then we get to line 16 again, decrement C. C is now 3, so we got 3 more bits to work with. Then we go to line 17, go back to line 6. C is 3, the Z flag is cleared, and the sign flag is also cleared. Line 7, JZI to L1. We're not going to branch. Go to line 8, add BB. So register B is now 8, so it is now 816. And as a result, the carry flag is cleared, sign flag is, Z flag is cleared, sign flag is cleared, overflow flag is cleared, and the L flag is cleared. Get to line 9, add AA. So register A is now 32. 32 plus 32 is 64. So we have the same deal here. Okay, so all of these flags are cleared. Oh wait, it's an AND operation. I mistook it as an add operation. Okay. Since it's an AND operation, A maintains its value of 32. The Z flag is cleared. The sign flag is cleared. Then we get to line 10. On line 10, the sign flag is not set, so we are not branching. And as a result, we go to line 11, which is unconditionally branching to L3. And then we get to line 15. We double A again, so this time A is 64. Carry flag is cleared. Z flag is cleared. Sign flag is cleared. Overflow flag is cleared. And then the L flag is also cleared. Go to line 16 with decrement C. C is now 2. We go to line 17, which branches back to line 6. So now line 6 is going to do the whole thing again. And CC, so C is 2, which means the 0 flag is cleared, the sign flag is also cleared. And then we get to line 7, we are not taking the conditional branch. We get to line 8, we add BB. So register B is 16, so it is now 32. And as a result, there's no carry, it is non-zero, it is not negative, there's no overflow, and there's no L flag. Then we get to line 9 and AA. A is 64, so A is 64. There's no 0 is cleared. The sign is also cleared. So we get to line 10. We do not perform the branch. We get to line 11. Then we continue on to line 15. We add A to A, so 64 plus 64 is 128. But this time you have to be super careful because the carry flag is cleared, the Z flag is cleared, sign flag is a 1, overflow is also a 1 because we're adding two non-negative values, but somehow we end up with the sign being a 1. So the L flag, which is always defined by the exclusive or between the sign and the overflow flag, is the L flag is going to be cleared as well. Then we get to line 16, decrement C. C is now 1. We get to line 17. Then we get back to line 6. And CC, so C is 1. So the Z flag is still cleared, and the sign flag is cleared. Line 7, we are not doing the conditional branch. We get to line 8, we add B to B. So register B was 32, so now it is 64. The sign carry flag is cleared, 0 flag is cleared, sign flag is cleared, overflow flag is cleared, and then the L flag is cleared. Go to line 9, we perform the AND operation based on A. So A is 128. So the Z flag is cleared, but the sign flag is a 1. So once again, we get into the conditional statement on line, we get to line 10 first. So line 10 then is followed by line 13. So we add D to B. D is, let's see, I think it's 8. Let me just double check. D is 8 indeed. So we are now adding D, register D, which is 8, to register B, which has 64. So that makes 72. Okay. And then we get to line 15. We add AA. So we add this A to A, and we get 0 back. Because 128 plus 128 is 256. But 256 requires 9 bits to represent, with the lowest 8 bits being 0. So that's the only portion we can store. So that's why register A is a 0. So this means the carry is going to be a 1 this time. The 0 flag is also going to be a 1. The sign flag is going to be cleared. The overflow flag is going to be a 1 because we're adding two negative values and somehow we get a non-negative value back. And the L flag is going to be a 1 because it's the exclusive OR between those two flags. Oh, I can see that you can't see the entire thing. Oh, okay, that's not good. Just need to move this around here. Ah, no. There we go. Okay, we need to move it a little bit more like that. Okay, now you can see the L flag. You were not able to see the L flag before. Okay, so we need one more page. Let's go to page add after. Okay, we are almost done, as you can probably tell. So after line 15, we got the line 16. Line 16 is decrementing register C. So register C is already a 1, so when we decrement, it becomes a 0. Then we get to line 17. Line 17 gets us back to line 6. Line 6 says, and CC. C equals to 0 as a result of that. This time Z is 1. The sign flag is cleared. So on line 7, we are in fact going for that branch to L1, which means we end up on line 19, and we are done. So as promised, this is actually a multiplication because 9 times 8 is 72, and register B in fact has 72 in it. So that's the end of the entire exam. So the last one is kind of long. So I'll give you partial credit if you don't finish. Basically, what I'll be looking at would be understanding of the various operations, when to branch, when not to branch, what flags get affected how, what operations perform, what. So I'll be giving partial credit for all the clues, of how those, of whether the flags are updated correctly. So if you cannot finish the trace with question number 5, it's okay. You still get partial credit based on what you have, based on how much you have turned in, and whether your partial submission reflects the understanding instructions, the flags, conditional branches, and etc. All right. So that's it. I'm gonna stop the streaming and make it available to you guys.